We are going to study tunneling. So the problem that we presented the previous week was the following. We had generically some potential. So this is the field V of x. This is done in one dimension, and I know that if I send in a classical particle, it can have different energies, kinetic energies at the beginning. It has a path, and if this particle will have an energy less than the height of this potential, it will be coming here, it will interact in a complicated way with this potential, and then it will go back. That means that if you go here, it's like when you run to the wall, you'll be reflected back. That's called reflection in a classical particle sense. On the other hand, if you come with an energy up here, so again, this scale is energy scale, then you'll simply go over, you'll be slowed down in a complicated way, but you will eventually go over, and if you have a detector here, eventually you'll find the particle. So in classical mechanics, either you are transmitted with probability 1, high energies, or you are reflected with probability 1, low energies. In quantum mechanics, what we are going to solve now are some incoming waves, which I denote by this wiggly sign. And these waves have also kinetic energy, and they will be waves, free waves, in the sense that they are eigenvalues of the momentum operator. That is, they will have here this type of structure. Some A is some amplitude. So big A means that there is a lot of weight for this guy. He is strong, so to say. And the K is the 1 over the wavelength. So you see, when this K will become when this K will become smaller, this wavelength will become bigger, etc. So this is just a figurative way to just show this thing. And you see here I have a plus. It's plus ik. So I think here about positive k. So the momentum is h bar k. Right? So h bar k is positive. In that sense, the arrow is in this direction. So it's a wave that is going in that direction, a free wave that is going into that direction. Now, in addition, I will have, so this is going to be called incoming wave, or element of the wave. And this is simply the reflected part. Now, the reflected part is denoted by E minus ikx. The minus sign represents the fact that now the momentum is going in the opposite direction. So now it's this part of the wave carries a negative momentum. So it's corresponding to the physical classical situation where the particle is reflected, and it will have here an amplitude. This amplitude here, which I will denote. I'll denote by B, is different than A, but notice that here I have the same K. So the way you need to think about these free waves, where are they valid? They are valid far away from this potential. So they are valid in a region where the potential V of x is simply a constant. So not close here. Here something complicated can happen. So these are asymptotic forms that are actually found far away to the left. In addition, far away to the right, we'll have you have something that is coming in, and then you will have something coming out, and this will be CEIK x. This guy that is coming out is also with wave vector k, the same wave vector k. In some sense, what is this wave vector k? This is an input to the theory. This corresponds to the energy that I come in with these waves. Why? Because a free wave, if you know its energy and you know its momentum is positive, you know exactly what is its k. Yeah? Because E equals h bar squared, k squared over 2m. This is a free particle here. So When I say I know the k, it means I prepare the system with some incoming wave with some specific energy E, corresponding to which you have a specific k. And you have here also a k, and this is because the potential here, V of x here and V of x here, is always going to be 0 here and 0 here. In the middle, it's going to be something else. In your homework assignment, you will have scattering not from something that starts at 0, but something that goes up and continues forever. And then this k will be different than this k. But for now, these k's are assumed to be all the same. And they are given by the energy, so I know what is k. What I don't know, I also know what is, in some sense, I know what is a. You will see later it's not so important. What am I asking? I want to know what is b, and I want to know what is c. The bigger is c, the more amplitude of wave coming out you have. The bigger is b, the more reflected part of the wave you have. So I would like to compute these two things and relate them to tunneling, the probability of tunneling or not, or tunneling or reflection. So in the last lesson, okay, so let us look at the incoming wave for a second, or this is just think about this as a free wave, some extended wave, EIK x, okay, and you have some amplitude A. In principle, you could have many components to this wave. So in principle, you could have here A of k, and then you have many k's, and you have to sum over all of them. But we are just treating one component. So in principle, if you want, you can have here A of k, but I'll omit that thing, and I'll think about 1k, and then I can write only 1a. So this amplitude can be a complex number, which is given by the incoming flux. Now, we calculated the probability current. The probability current, I just remind you, we showed that there is the density, the wave function, square amplitude, the square of the wave function is a probability density. And then what we said is, if you have some probability density, the probability to have the particle somewhere in space, it changes in time. And how does it change in time? You have some current coming in to this region, and then you have some current going out of that region. And then the change in the current, the div j, will be equal to the change in the density of particles in this region. So it was just conservation, like conservation of mass. If you have here, you want to know how many particles, atoms are inside here. What you need to know is the current coming in to this volume and the current coming out. And similarly in quantum mechanics, but you're not talking about mass, you're talking about probability densities, which corresponds to the fact that the particle has a probabilistic meaning. So in this thing, we have this current in one dimension, which was calculated last week, and this is simply given by this formula. I'm not going to repeat the derivation. Psi d over dx psi. So you have here something which is not immediately intuitive, but you have this type of current, and then you have the complex conjugate of this guy, psi star d psi dx. So to build some intuition for this current, let us just, this was done also previous week, we just let us plug in this type of incoming wave, and then let us see what is happening here. So you have h over 2mi, psi star is a star, and okay, you have always a star, and from here you have a, and here it will be the opposite, and the derivative doesn't act on a does not depend on position. So you'll have a star times a, and then inside here you'll have e I k x, and when I take the derivative with respect to x, I get here I k e I k x, then I have minus e I k x, And the derivative now, I take the derivative of the complex conjugate. The complex conjugate has a minus here. So here I get minus I k e to the minus I kx. So you see that this is some exponential, and you have this phase here, but this is exactly the opposite in the sense this is minus, this is plus, so they cancel down in the exponent. And then you see here minus minus, so you get 2k, and you have the I will cancel with this I, and the 2 will cancel with this guy. So the j, after you do this, you find this expression over m. It is, all this is somewhat similar to what you saw maybe previously in wave mechanics, when you have scattering of wave in electromagnetic waves. There you have one material, and then you have another material, and another material. You plug in a wave that satisfies the wave equation, and you have these type of things. The difference here is possibly that you see here you have the velocity, and the velocity in the sense that this is the momentum, h bar k is like the momentum, according to de Broglie. Over m, this is the velocity, so it's very natural that the current, that is how much is coming into some region, is proportional to the velocity. The faster you are, the more current you have. This is very natural, and of course the current is proportional to a squared. Well, obviously if a, for example, would be 0, you will have no current. The bigger is a, the more current you have, so it's natural. And of course, we cannot have here something proportional to a. It has to be a square in some sense, because in quantum mechanics, everything is not an amplitude, but a square, if you want to look at real things, not imaginary things. So, okay, so this is the definition of the current. If you want to see, this is the current of particles coming outside here, coming here, and then you have a current going back. When I mean particles, I go into some picture in my mind where I throw in many particles, like in an experiment, but they are not interacting, of course, one with another. And then you have a current of real particles coming in. Some of them are reflected, some of them transmitted, and I can somehow in an experiment count this. But we will take this definition, intuitive or not, and let us now define we would like to define the transmission coefficient T. So transmission coefficient is equal to what is coming out, J out. This is, here I have J out over J in. And when I mean J in, I mean the part of the current that is related to A, only this incoming wave with the vector K. Now, this guy is simply given by these amplitudes, you see, C and A. Why? Because here I'm using the fact that I have here H bar K over M, H bar K over M. So here I'm using the fact that the potential here and here is 0, so you have the same K on both sides. You didn't have some step. So these two guys will cancel, of course, and J out is equal to C squared, and J in is equal to A squared. So the transmission probability, this guy is called transmission coefficient. The transmission probability is equal to C squared over A squared. This number has no dimensions. It's dimensionless. That's why I could call it a probability. And it is between 0 and 1. One can show it's between 0 and 1. It's very natural, because if something is coming in, some part of it is reflected, not everything goes out. You don't create particles here in the middle, so this C absolute value squared is less than A squared. Notice that here we do not care about the question about what exactly is C and what exactly is A, but we care about the ratio between them two. And why is that? Because it doesn't matter, let's say you in a real experiment, you plugged in, you throw into the system 1 billion particles, and then another experiment you plug in 1 billion times 10. What you care about is the number of guys going through relative to the number that come in. So you look for some quantity that doesn't depend on the intensity of the wave, so to speak. We don't care about A by itself, but on the ratios. Because A is not universal, and that will depend on a specific experiment. So, and we have this type of expression. Similarly, we define the R, which is the reflection coefficient or probability. This is J reflected, J in. And J reflected, well, you understand, I think, by now, this is related to J reflected. This is equal, under the same conditions, to B squared over A squared. So let us write it here. This is B squared over A squared. And similarly, of course, in the same way, like for T, we have R greater or equal to 0, and in fact, R plus T, that's a little bit less trivial, is equal 1. So this means that the total probability of being transmitted is simply 1 minus the total probability of being reflected. I'm not proving this. You can do for the example that I calculate today. You can simply calculate R. We will calculate only T. And then you can check this, and you can prove it very generally also. So I'm not going to prove this, but physically this is reasonable that R plus T equal 1. This is nice because it just allows you to calculate one of them. I'll calculate T and then I know R. I don't need to do both. That's good news because I don't like to calculate things. Again, the mindset is that if I want to have T, there is a classical, this is a quantum mechanical object. I compare it to the classical T. So let us assume now that our potential, we're going to solve a simple potential, that it has a V0. So this is, again, this is X. You come in with a classical particle. Then if it has an energy, I'll plot it as a function of energy. Then if the energy is less than this V0, V0 is positive, then the transmission probability is 0 because you come here, then you go back. So I have here 0. And then if I come with an energy bigger than V0, probability of being transmitted is 1. So it is a very sharp step function in classical mechanics. And our goal is to show that in quantum mechanics, you have a different behavior. Especially that in this region, while the probability here is 0 strictly in classical mechanics, we will show that here you can tunnel, which means you can go, so to say, through this channel, through this potential, and the T here will be not 0. We will see exactly what it is in one example at least. Okay, this is our goal. Do you have any questions? So now instead of discussing the general setting, let us discuss a particular case and solve it, or more or less solve it. What I mean by that is I'll solve it until the algebra will become ugly, and then I'll leave that to you. So our goal is to find T for the potential V of x equal V0 when x is between minus A and A, otherwise it's 0. So this is a step potential. The potential looks like this. So this is minus A, this is A, this is the x coordinate, this is V0. V0 is positive. This is how our potential looks like. It's a step-like potential. This allows me, why is this very convenient to solve? You immediately understand. The classical problem here is really trivial because this allows me to solve this. Okay, this is a free wave up till here. And here there's another free wave, and in the middle there's going to be something simple. The structure of the potential is very simple. That's why we choose it. That's why we teach it. If it would have this complicated structure, we could not solve it as usual. We could solve it numerically, but not as we do here. As mentioned already, we have here an incoming wave, AEIKX. We have here a reflected wave that was C minus IKX. And over here, we had the transmitted wave, what goes out. Just I mixed it up, of course. This was B and this was C. Sorry. Yes?
Why A isn't 1?
You can take it to 1. That's actually what I'm saying here. Because eventually what I calculate is something, C will depend on A. The bigger A is, C will be proportional to it. So, and eventually it will cancel. The reason why I don't take it to 1 is the following. This is I briefly mentioned, because if you want to treat here a wave packet that doesn't have only one component of the wave, then I mentioned before that I can have here A of K. And then one wave, 1K, will have 1AK. So for example, consider that you have a Gaussian packet and it's going in this direction. This Gaussian packet, if you understood my class from 2 or 3 lessons ago, is decomposed into a linear combination of 3 waves, IKX, and each one of them has some amplitude. That was the function G of K, if you remember, which now I call A of K. So each wave has a different amplitude inside. So you have to weigh it. So for that you need some AK, and then you need to sum over all the AKs. Because in generality you don't have 1K. But I want to solve only 1K, but in generality you can have more than 1K. You throw in something like a packet. Okay? But for the sake of this class, yeah, you can think about, okay, this A is 1. There is another reason is that actually there is a problem that we hide under the carpet. What is the problem? That you have a free wave, EIKX. Forget about the potential. This wave by itself is not a legitimate wave in quantum mechanics. The reason is that the square of it is a constant. And if it goes from minus infinity to infinity, it's not normalized. So the way to treat it correctly is actually you add some boundary condition here and here in a finite system. So actually in a real system, A, the wave function has units in one dimension of 1 over square root of meter, because it's a probability density. And that's why if you just plug in A1 is a bit misleading, because there are units to psi. Yeah? So you are right. On the mathematical side, A doesn't matter because eventually it will cancel out here. On the physical side, A has units. I don't like to take it 1, and if you have, but for the sake of this lesson, you can think about A equal 1, it's fine. Okay, so I have this, setting, and of course I have here 3 regions. These 3 regions, how do I do it from left to right, I guess? Yes. I'll call this region 1, I'll call this region 2, and I'll call this region 3. This region 3 is for x bigger than a. This is between minus a and a. Later on, we're going to change the value of a. Let's say, let's make this very, very thin. We're going to ask, is it easy to be transmitted when a is small? Is it easier? Is it going to be easier to be transmitted through something small? Well, you can guess. The answer will be yes, but it also depends on the details. Okay, so we want to do this, and we are solving. How do we solve this? How do we find connection between A, B, and C? What we are solving is the time-independent Schrödinger equation. This phi is actually these waves. Phi of x plus v of x times phi of x equals e phi of x where in this problem it's not an eigenvalue problem. We know what is the E, as I said before. This is E related to this K. It's some number. That's the energy of the incoming particles that you plug in. And you have here a stationary solution of this state, and we want to just calculate this state. If you want to think about it as differently, a little bit differently, what you really have here is, I will add here plus I omega t. Here. Plus I omega t, and also here I omega t. But when I calculate all these b squareds and c squares, absolute value square, that will go away. So the time goes away. It's a stationary state. I know the energy, so I don't need to treat it, and I just need to take this eigenmode of the Schrödinger equation, the time-independent Schrödinger equation. I don't need to think about time. Of course, if I would put in a wave packet and it will evolve, then time would come into detail. It would be much more complicated. But here, I simply can ignore it, and then, okay, if you want to think about it, this is fluctuating in time, but who cares? In our case, it doesn't matter because of these squares up here, both here and here. Okay, so this is the equation that we would like to solve, and we have 3 regions. There are 2, all the regions are trivial, but 2 of them are in particular trivial. So, if I set E equal h bar k squared over 2m, which is simply momentum squared over m, that's simply the de Broglie. I just put it here, just representing the k and the e in some different numbers. So again, if I know e, I know k. K is given. Or if I can say I know k, so I know e, it's the same thing. If I represent it like this, then it's very easy to solve in region one and 3. Why is it trivial? Because, okay, in region 1 and 3, the potential here is 0. So I get a really simple equation that I will even not write down because it's trivial, right? So, I mean, then you get the solution phi of x in these two regions, which is exactly what I wrote. These are the waves. I have here E, A, E, I, Kx plus B, E minus I, Kx. This is in region 1. And then in region 3, I have C, E, I, Kx. That's in region 3. Why is this the case? Because it's very simple. In the Schrödinger equation, I have here the second derivative of this guy. The second derivative of this guy gives you minus k squared. So here I'll get minus k squared. The minus will cancel. I have here h bar k squared, and that will be exactly the energy because this potential is 0 in these regions. Here and here, the potential is 0. No field, no potential field. What is the solution in region 3, in region 2? It's as nearly as simple. You have minus h bar, this is the Schrödinger equation. Second derivative with respect to x squared, phi, that's the kinetic energy operator, the usual one. Here I have plus V0. V0 is a constant, some number, that's the scale of energy in this problem. V equals E phi. And this E is the same as before. It's the energy of the incoming wave. This is not more complicated than what we had before. I can write this. Let us move this to the other side. Let us move this to the other side. Also, this guy we're going to move to the other side, and then we'll have, and we're going to multiply by 2m over h bar. So we'll have 0, the second derivative of x squared phi is equal to 2 plus, I'm going to write it, 2m over h bar squared. This is because I multiplied by this factor. I moved it here. And here I'll have E minus V phi. So this is another trivial equation. Now I can consider two cases, either E bigger than V. So E bigger than V, I come with the energy E, which is bigger than V. This is E bigger than V. I can also consider a case, we will consider both, E less than V. Again, V is the height of the potential. Let us denote, we will consider simply the case E less than V, and then we will go also to the other solution. If E is less than V, then all this guy is a positive thing. And then I'm going to write this as in terms of kappa. Kappa is like K, but it will denote something. It will not be a wave vector. It will be some decaying mode. I'll soon explain. And this I define as 2m V minus E. So again, here V greater than E. If V greater than E, this kappa is a real number. It's positive real number. All this divided by h bar. So now I'm concentrating on this solution, and then kappa is like this. And notice that I switch this. So let us do the math, and then I'll explain what is the meaning of the physics. So the equation is simple. Minus kappa squared phi. What are the solutions of this thing if kappa is real? What are the solutions? You will have two solutions. So phi in region 2 of x is equal to b plus exponential kx plus b minus exponential minus kappa x. This is the solution in region 2. And I had already the solutions in region 1 and 3. Please, in your notebooks, add the index. Here I have 2. In your notebook, go backwards and add 1 and 3 in the appropriate place. So 1 is x less than minus a. We will call this is the wave function in region 2. So what is going on here essentially? Well, you see immediately why this is a solution. If you take this, you take the derivative twice, what will you get? Kappa squared. If I take the minus 1 minus kappa squared, I'll get this, and this equation will trivially be satisfied. But you see what you get here. You get here some exponentials. Up until now in quantum mechanics, you were used to get exponentials, but you had not kappa, you had ik. Those were free waves. What are these type of waves? They're kind of waves. What is happening is the following. Outside here, I've just denoted by a picturesque way, you have some oscillating solution. EIKX, it can be positive, it can be negative. Here you have solutions which I want to denote by decay or rise. The rise means plus k, and the minus means it decays. So, but you can plot just one of them. What is happening here? When I have in a classical world, you have here some momentum. Then you have EIKX, that's the wave, the quantum wave. Then in a classical world, you are not allowed at all to come inside here. So these waves, when they continue into this not allowed region, they turn from oscillating waves to decaying or exploding waves. And again, they will not exist at all in a classical world. So this is actually related to this tunneling, because you are here in a region which is not allowed at all from classical point of view. Why is it not allowed? Because you see I'm working here with V greater than E. And that's why I drew this wave down here, so you can understand that the energy is lower than this height. And then you have these decaying modes. Now, let us imagine that this thing would continue forever. Then what would happen? You'll have one decaying thing. This, you see here, this one is decaying at infinity. This one is exploding at infinity. So let us assume this would continue forever. What would you get here? You would get both of them. You'd have to get rid of one. Why would you get rid of one? Because of the boundary at infinity. You would say, this guy that is exploding at plus infinity here, if this would continue, this is not allowed, and then you'll have something that is simply decaying. And that means that if you had only if this would continue forever, this would just decay, this part of the wave. And then, okay, you go inside, but you are allowed to go inside, but only a little bit, because it decays exponentially inside here. But here I can have both plus and minus. Why? Because this is of finite length. So out here, okay, this just continues. It goes up, but it doesn't go to infinity, and then everything's okay. And here I'll continue it, and then you'll see the boundary condition, etc. But these decaying modes are very natural. You'll see them in many problems. For example, if you have a kind of potential like this, or anything, maybe a potential like this, you will always find here and here, when you look at the lowest energy values, some decaying modes in the forbidden area classically. These are the wave function, the end of the wave function that decays. Here it decays exponentially, but it can decay faster or slower. But this going into this disallowed region is something very natural in quantum mechanics. Okay, so this is the first time you saw these type of modes. And now I need to solve this thing. How do I solve it? So, I mean, I solved it, but I don't know what is B minus. I don't know what is B plus. I don't know what is C, and I don't know what is B. I don't know what is A. But so I have 5 parameters in this problem. Let us write them down. I have A, I have B, I have C, I have B plus, and I have B minus. These are unknowns. What do I know? I know kappa, I know k. I mean, I know kappa because someone told me what is the potential V, so I know kappa and I know k, and this is the same as saying that I know things like E, of course I know the mass, etc. I said A is not relevant, so you're right, I can take A equal 1 because eventually this will cancel out. So, because what I said before, I have 5 variables. In principle, if I had to determine A, I had to have how many equations? 5. 5 unknowns, 5 equations. But actually, I will have only 4 because we are only looking at ratios. So you can say A is normalization constant, so we can forget about it. Okay, so I need 4 equations. So what are these 4 equations to determine these parameters? Anyone has any idea?
As x equals to minus a and x equals to a, it should be continuous.
Right. So what you are saying, I just repeat. So I have here some boundary, minus a, and the wave function should be continuous also on this point and also on that point. That is 2 equations. I'm going to write them down soon. That's not enough. That's not enough to determine all these parameters. What else do I need?
Decay.
What?
Maybe the decaying after the...
The decaying. I wrote here, they are decaying. I know everything about the I know kappa, I know this fine. I don't know. So, I mean, yeah, they are decaying, you are right, but that doesn't help me.
Boundary at infinity?
What?
Boundary at infinity?
Boundary at infinity, no, because these are perfectly fine incoming waves from infinity and infinity. If I had here plus kappa, I would be worried that the solution diverges. Or to put it differently, I already used the boundary at infinity. Because in principle, mathematically, I could add here d e minus ikx. Yes? This, if I add this to the Schrödinger equation in this region 3, it is a solution. I already canceled this. I didn't tell you this because for me, okay, I thought this cost too many times, so I forgot to tell you. I canceled that term because of the boundary condition at infinity. I assume that you have something coming in from minus infinity, this is A, something reflected, and something transmitted, and this D is 0. So we already used the boundary at infinity. Any other ideas? So what else? First derivative here, continuous wave function, correct. Second time, correct. Continuous wave function on these 2 points. And we also need to demand that the derivative of phi on x plus minus a is continuous. I'll explain why, and we will see soon the context later. So, because we have 2 boundaries, we have 2 conditions, so 2 times 2 is 4, and then if I write down the equations, I'll be able, in principle, to solve all this mess. So, physically and intuitively, we can expect that these conditions are valid, and we also talked about them already. First of all, it's obvious that they are valid far away from the boundary. These are automatic. The derivative, the wave function is continuous. It's a function, it's analytical, etc. We only need to take care of that it doesn't do something strange on the boundary. This you can understand from physics and later from math. Simply think about this. This is not the real potential, but the potential is something like this. Something smooth. You see, this potential is not real physics because you have a discontinuity in the derivative, but let's say you have a real potential which is nearly like that, then the potential is smooth, and then you expect that the wave function will not make suddenly a jump. What will create a jump? That's not physical. The wave function cannot be discontinuous. And it's also derivative cannot be discontinuous, because if the derivative is discontinuous, then you will have problem with kinetic energy, because that's the second derivative at the point. So generally speaking, physics demands that everything is smooth and nice, and then first order derivative is continuous, and the second order one is also continuous. We will later prove this if you also want to mathematical proof that this has to be. There is an exception. What is the exception? Just to show that this is not trivial, not totally mathematically trivial. When is the derivative of the wave function not continuous? Maybe, yes?
Maybe if you have like a particle in a box and the potential goes to infinity.
Right, so yes, that's one example. And I think another example, you solve particle in a delta function. We will soon show you why. So if the potential goes suddenly to infinity, either in a box or a delta function, the potential is a delta function. Now, of course, in real physics, there's no such thing as a delta function potential, but in homework assignments and exams, we like to give you delta functions, because you solve, these are the exceptions where the derivative of the wave function is not continuous. As he mentioned, for a box, you have a box, then okay, on one side of the box, the derivative is something, and then the wave function is 0, so the derivative is also 0, so it's not continuous. This is because suddenly the potential goes to infinity. Here the potential doesn't go to infinity, so the derivative of the wave function is going to be continuous. So as long as V, the potential is not infinity, then the derivative of the wave function and the wave function itself is continuous. And this is our case at least. Okay, so we're going to solve this now. And okay, let us leave this. Solve this, solve. I'm going to write down the lovely equations. Oops, that's classical mechanics. I think if I try to do it 20 times, I'll not succeed. Okay. So the boundary conditions, just let us write them down. So I have phi 1, a minus. The minus means minus epsilon here. This is a minus. It's a minus some epsilon, if you want to be strict. Wait, what was no, this was 1, right? This is 2 and this is 3. So, okay, this is minus with a minus, because this point is minus a. This is equal to phi 2. So phi 1, to remind you, that was the free wave coming in, reflecting, transmission. This guy was in the middle where you had the decaying modes. So this will relate between what you have on the left and what you have in the middle. And this guy is minus a plus. Then you have phi 1 derivative at point A. I will not write this minus anymore, but this is what it means. The derivative okay, here I will write it, and then I have phi 2 at point A. This will come from the minus, because now I'm at this point, so phi 2a minus. This is not, you see, this is this point here. This is equal to phi 3a plus, and then phi 2a derivative equal phi 3a derivative. These are the 4 equations generally. You can immediately understand that if I have some potential like this, I'll have many more boundary conditions. So we are lucky that we are solving a simple box and not something complicated like that. Okay, so let us translate this into equations. Okay, so mathematically, why is the derivative continuous? I assume that the derivative phi itself is trivial from physics point of view, or I'll put this a bit differently. When is the derivative continuous? So let us look at the Schrödinger equation. I have 2m h plus v of x phi. This is equal e. This is in general. This is not only for our problem. This is general, completely general. Now, how will I look at the continuity? I'll integrate this equation from, let's say, a minus eta to a plus eta. And eta goes to 0. So I look at some small region. This is my a, and I integrate it between these 2 points. This is a minus eta. This is a plus eta. And I integrate in our problem, but this is general. So when I do that, I have simply from a minus eta, a plus eta, minus h bar 2m d dx squared phi dx plus a minus eta, a plus eta, v of x times phi dx integral a minus eta, a plus eta, e phi of x dx. Now, let us look at these integrals. Phi of x is this integral when eta goes to 0. This goes to 0. Because, I mean, phi of x, this is approximately energy, which is some number, phi of a times 2 delta. This is what I assume. So when times eta. So this goes to 0 when eta goes to 0. What is this guy? Well, if v of x is not infinity, like in a delta function, if we had here a delta function, then we would have a different ballgame. But if it's not a delta function, or v of x is not infinity in some sense, okay, v of x in this region, okay, it's 2 joule, whatever it is. Then you have approximately, this is v of a, this is approximately phi of a, and then the integral when eta is going to 0 is going to 0. So this also goes to 0. And when you do homework with a delta function, then you will see, you plug in a delta function, then you'll get a condition. Because what is this guy? This is the second derivative of x with respect to phi. But what is that? This is simply d over dx phi at a plus delta minus d over the phi dx a minus delta. And because all the other guys are 0, this guy is 0 because the potential is not exploding. This guy is 0, so also the derivative has to be continuous. This is the meaning of continuous. So some small eta, the derivative of the a plus eta is the same as the derivative as a minus eta. Okay, so now let us go to the boundary conditions. So just to remind you, here I have minus A. So let us start with the wave. Here I have these two waves coming in. So this one, phi 1 at A minus and A plus, around this point. I have here A, E minus I K A. So remember, the incoming wave was E I K X. Now I plug in minus A. So this plus X turns into minus A. That's the wave function just here. And then here I have a minus K, so this guy will be B E I K A. Because I'm working on this point minus A, and this is equal, we had the B plus exponential. I'm working at minus A, so I had kappa times X, so now I have minus kappa times A plus B minus exponential plus kappa A. So just notice that the B plus goes with the minus and the minus goes with the plus because I'm working at point A, X equal minus A. So this is the phi 1, phi 2 at minus A. Now the derivative. So when I take the derivative of this function, I get IK out. So then I get A. I'm going to write the IK outside. I take the derivative, so I get IK, then I get A, the same thing as I have here. When I take the derivative of the wave that is going out, so what will I have here? I'll have a minus. I'll have a minus because I take the derivative of the minus, this wave function. So here I have this minus B E I K A. And similar thing will happen here. The solution inside here, I remind you, it was exponentials with kappa x and minus kappa x. So when I take derivatives here, in this region, what is the derivative of an exponential? You get the kappa times the exponential. Doesn't matter if you have a plus, you have a plus and you have a minus. But so eventually you have this kappa, which is related to the potential V0. And here I get B plus E minus kappa A. And here I had a minus B minus E kappa A. If you don't see this, do it yourself. Then I have region 2A, continuity of the wave function. It's somewhat nicer because out here I have only one wave. So I have C E I K A. This was because I have plus A and this was E I K X. So just plug in A. This is equal to B plus. Now I need to calculate B plus not on minus A but on plus A, so it's exponential kappa times A plus B minus exponential kappa A. And then I need to take the derivatives at this point. So when I take the derivative, I get the IK like I had here. So this is C I K E I K A. Please distinguish between K and kappa. They look the same, but they are not. Here I have this big kappa, B plus exponent kappa A. And this guy had a minus, so when I take the derivative, I'll get minus kappa. This is the kappa outside here. And then I'll have minus B minus exponential minus kappa A. So what we are after actually is we are after actually B and C. So the first thing to do is we have here in this equation B plus and B minus. So the first thing to do is isolate B plus and B minus. For example, you want to get rid of them, so multiply this equation by kappa plus and then subtract them, etc. to get rid of B plus, and then you get rid of B minus, and then you get some equation which involves A, B, and C. These are, if you think about A as a constant, these are 4 equations with 4 unknowns. You can solve this. It's a lot of algebra. I'm not doing it. You should do it. I actually did it a long time ago. So I'm not going to go into all the details, but you see here I did it. It's 2 pages of algebra, but it's not so bad. After you do those 2 pages of algebra, eventually you get something which I'm going to call tau. And tau is C over A. This is C over A is the transmission amplitude. Not a probability, but an amplitude. It is a complex number. It has a phase, it has a strength, but it also has a phase. After you do that, what we really want is T is tau absolute value squared. Because that is what we are after, C squared over A squared. Also this step can involve mistakes, taking the absolute value squared of some complicated complex function is not so pleasant. The phase has some meaning, but we will not discuss it. All of you, by yourself, you should solve this. It will take you some time, but not so bad. So for example, what I found for C over A is 2e minus ka 1 plus kappa 2ik ik over kappa e minus 2 kappa a plus I ka plus 1 minus kappa 2ik minus ik over kappa 2 kappa a plus ika. You don't need to remember this, of course, just to show that the solution looks a bit ugly. It's not trivial because you have 4 equations and 4 unknowns. This is to be expected. More importantly, we are going to write the square of this, and we're going to focus on this, and then go. Here I have it in terms of kappa and k, and then you need to go from kappa and k to energy. It's easier to present the solution that way. And so after doing that, so from here, after some work, we get the final solution. It's 1 plus v squared for e minus v squared, v0. v0 is the size of the potential, sine hyperbole squared of 2m v0 minus e a over h bar. This is wrong. Here I switched it. This is for V0 bigger than E. immediately you have a sanity check, and that is this number is indeed less than 1. Because you have 1 plus something, V0 is bigger than E. This is how I found my mistake. I wrote it like that, and then it would be bad, because that could be negative and as big as you want. So you see here I have some positive number. E is bigger than 0. V0 is bigger than E. All this is positive. Sine hyperbole is also positive. So this is a number bigger than 1. So you have 1 over 1 plus a number bigger than 1. All this is smaller than unity. So this is smaller than 1. And it's also obvious that this guy is bigger than 0 because everything here is positive. So this is indeed some check that you can do, that at least the transmission probability is a probability in the sense that it is something between 0 and 1. Okay, so let us summarize the properties of this equation that gives you the transmission probability in terms of the height of the potential, in terms of the energy that you insert into the incoming wave, of course the mass and the width A of the potential field. So, as mentioned already, you can repeat this calculation also for the coefficient C, and you can calculate and show that T is also equal 1 minus R. So by concentrating on the transmission coefficient, it's exactly the same thing as saying that I know also the reflection. So I just want to say what is going past the potential step, but it's the same as saying all the rest is coming back. So we will concentrate only on the potential first. So first of all, just to remind you, we have here the Sinch hyperbole. This, if you don't remember, this is e to the x minus e to the minus x over 2. For example, for small x, then you can expand it, and then this is like the expansion of sine x. So this means that when this guy becomes big, so we will see when this thing becomes big, then you will have here an exponential of this big factor and minus e to the minus this big factor. So the decaying part of the exponential will go, so for large x, this goes like e to the power x over 2 for large x. X is just a dummy variable. It's nothing to do with space that we had before. The x can be anything. This is just a function. So if you don't like x, write here y. So what will happen for the case that 2 times the square root of 2m v minus e a over h bar is much, much bigger than 1. So first of all, this parameter that you have inside has no units. This is easily seen from, this comes from the wave kappa, essentially. This has no units, of course, this is dimensionless. And I want to look at the case where this guy is big, and then I can approximate this Hine hyperbole with a simple function exponential. But what does it mean that this function, this condition holds? What does it mean? Well, roughly speaking, when does this hold? Can you see what is the meaning of this being big? Well, it means many things, but in one word, what does it mean? What?
That V is much bigger than E.
Yeah, but V much bigger than E is in some sense meaningless because that depends on what units you are measuring V. So you measure them in joule, electric volt. So intuitively, this is, you can either have this guy very big, this guy very big in some sense, but you need all of them to get a dimensionless quantity. But essentially, this is what we call the classical limit. Why is this the classical world? Because, for example, a big mass, in some sense. So if you have 1 kilogram, What I mean by that, this is a little bit not exact in the sense that provided that these guys are not too small, right? If you have a very big mass, if h bar in some meaningful way goes to 0, which I explained to you, that is the classical limit where you don't, physics with no h bar is classical physics. Of course, when A goes to infinity, so this is big, what does it mean? It means that you have something very fat to cross. So it's very difficult to cross it. And that's why, because our energy here is always less than V0. So I'm coming here and I have something very wide. It will be very difficult to cross. And essentially also when E is very small, let's say V0 is big and E is not close to V0. So when I come here and I come with very low energies and V0 is big, then this prefactor is big. All these mean some classical limit because what you expect in these cases, and soon we will see, what do you expect of T? T will be in the classical limit, it will be very small, because in the classical limit, if you come with some energy which is less than V0, then there's no transmission, everything goes back. So all these conditions imply a classical limit of what we are intuitively expecting from a classical particle. But we can go one step further. So in classical mechanics, T is 0. But now we can say T is small, but what is it exactly? We can do this. And this we simply do by taking this sine hyperbole, and we're going to approximate it by exponential of this guy over 2, all this squared. Okay, so you understand from this asymptotic limit. So when that condition holds, then in this case, the transmission coefficient is small, and it's given by, okay, from the sine hyperbole, remember I have e to the power x over 2, then I'll have here 2 squared, I have this 4, then I'll get 16 e V0 minus e over V0, because this 1 is not important, because all this is huge, exponentially huge, so this guy I can neglect. And then when I divide it, this simply comes upstairs, right? And here I'll have exponential of, here I have to the power 2, so this exponential, so all this junk, but multiplied by 2. With a minus sign, because it was downstairs and now I'm putting it upstairs. So here I have 4 to m V0 minus e a over h bar. And this is much smaller than 1 because of this minus term. It's exponentially small in this big parameter. This is a big parameter. Only when this guy is big is this simplified equation. So this is big. The exponential of a minus big thing is small. So in this case, I get this type of behavior. And what do I see in this limit? Is that, for example, I can take a sample of some material that has some higher potential than the material that is found here and here. And this material is already thick, many atoms here, and I can bring some particles here, and they will partly be reflected to the other side. Now this is roughly 2a. Now I'll make it bigger, twice as bigger. This you can do because you can build in a laboratory, you can build some device, and this has size 2a. Now I'll make it size 4a. And I'll do the same experiment with the same incoming energy. And then you'll see that the number of particles, assuming that the incoming particles, the number of them are the same in the two experiments, as a function of A is simply decaying. Of course, A, you cannot start from 0. When A is big enough, it decays exponentially to A. So you can go to the lab and fabricate bigger and bigger systems, and you can check this by making the system bigger. You can control this A quite easily. For example, mass is difficult to control. H bar is difficult to control. V0 and A and E are something that you can play around with, and you can control this and see that, you know, this current of particles will decay exponentially. So this is number of particles transmitted. It is decaying like A times C. C is all the other junk. There is a special point here. So all this just says, okay, the classical guy was 0. This guy is very small. When H bar goes to 0, this is also 0. So this is something very small. If you want to find an effect in the laboratory, you want to make this transmission coefficient big so you can measure it, right? Bigger as possible. But still working in the classical regime where E is less than V0. So where do you expect to get a bigger effect, still under the conditions of the game that we are playing now? So let us start plotting this. This is as a function of energy, and I plot T. And let us assume that this condition holds at least when E is much, much smaller than V0. So here you get something that is nearly 0, and it's starting to increase because I take E and I make it closer to V0. So this slowly increases. And because of this solution, which is a sine hyperbole, there's no oscillations, there's no thing. Essentially, it's kind of a smooth function. So this goes up. So you kind of expect that when V0 is close to E, then the biggest effect will happen because you have the more energy. It's kind of natural because the classical particle comes above here when V is bigger than 0. So, okay, the classical particle is a step thing. This is the classical particle. This thing is the step, is the classical, right? This guy is the classical. So the maximum here will be on this point. So let us investigate this point. I take just V0 equal E. There is a slight problem, you see, because V0 equal E, you get here 0. Sine hyperbole of 0 is 0. That's okay, but you see downstairs here I also get 0. So what I get here is a 0 times 0. 0 over 0. Right? So, but what is the sine hyperbole close to when this guy is small? It's this argument when it's small, right? Because sine hyperbole, when x is small, is x. So what happens, you see, you have here the square root. When I square it, you have V0 minus E will cancel exactly this V0 minus E. This is just L'Hopital rule when I take the limit E going to V0. So using the L'Hopital rule, I'll get T at E equal V0 as 1 plus V0 over 4E, but E is V0. This is this guy. Okay, let us write it. V0 minus E times this thing, 2 square root 2m V0 minus E, A over H bar. What do I need to do now? To the power 2, this is this guy. And that's it. Okay, then this guy will cancel, this guy will cancel, this 2 will cancel with this 4. This V0 is the same as this. Yeah, but here I have a mistake. This is V0 squared because of this V0 squared. So V0 over E, one of them will cancel. And then this guy is equal to the following: 1 plus 1 plus 2m a squared over h bar v. This is h bar squared because here I have h bar squared. You see immediately this has units of 1 over energy, so the units here are dimensionless. This is good and this is okay. So here I calculated the value of this guy. So the value of this guy depends what is V, what is M, etc. It can be many things, but it's this particular value. And then more or less I have this type of behavior when I go. And all this region is what I call the tunneling region. This is tunneling because the energy is less than V0. So here I have energy less than V0. Classically, this was this step function. 0, classical, something finite when you have quantum mechanics. What will happen now when E is bigger than V0? So you have a scattering like this. This is V0, and I come with a higher energy. So what is the solution? What do you need to do? How do you solve this now? What?
Isn't it fully transmitted?
No, it's not. Okay, that is the physical question. The physical question is, in the classical world, now t equal 1. We will show that there is 2 surprises. One, that here the quantum world transmission is more than 1. The second surprise is going to be, I'm going to ruin it, that here in the classical part, the transmission can be less than 1. It's the opposite, but both of them are surprising in the same way. We are more surprised by this part, because this part somehow infers that the energy of the particle is, the kinetic energy is like below the potential energy, and that means that negative energy. So this tunneling is really mind-boggling, but also this part that, okay, here it can be less than 1 is also very interesting, a quantum effect as well. But how will we solve it technically? What will we do? What is the way to solve this? What will be the difference than what we did up to now?
We have an imaginary kappa, no?
What?
Lots of minuses.
Lots of minuses. It's a lot of hard work, right? That's what you're saying. Kappa will become imaginary.
But we'd have to change V0 minus E to E minus V0, and it would start cascades with lots of minuses.
Lots of minuses. Okay, I claim no. There's a simpler way. You simply take this, and you say it's okay. You continue with this. And then what will happen? The sine hyperbole, what will happen? It will turn into minus I sine. We'll soon do that. And then you'll get the correct solution. You can more or less see this, because I said kappa, is positive, but okay, it has a square root of something. Now let us continue to let it be imaginary. Continue all the way. And if you follow all the roots, then you will see that the only thing you need to change here is change this. So what will happen? This sine hyperbole will change into a sine, an oscillating function. Instead of an exponential type of function, you'll have here an oscillating function. So generally speaking, from the definition of sine hyperbole, so sine hyperbole of, you see here I get this will become a complex number, right? Because I have here minus, I'm going to switch this. Then Then Ix, generally this is Eix minus E minus Ix over 2. This I guess you saw somewhere. And what is this guy? This is I sine X. Yes. Right? So you get this I, and then when you have this I, when you take the minus, it will, the I square will be minus, and but then you're going to switch these two guys. And then if I do all that, okay, so sine hyperbole goes into I sine in this thing. And then I get in the denominator is what you have here. In the denominator, I get sine squared. We don't care so much about the sine, but 2m e minus v0 a over h bar. I switch this sign, yeah, because I switch it, and then I have this in the original minus, and that gives you the sine hyperbole. So what do I get here? I get 1 something times the sine function plus 1. When do I get t equal 1? When do I get full transmission? When do I get full transmission? Now it's easy. Well, when this sine is equal 0, right? So condition for resonance. What do I mean by resonance? It's simple. T equal 1 is the sine, which we had here, is equal 0. When this is equal 0, T is equal 1. So these are special energy. What does it mean? There are special energies that I let the particles come inside the system with some special energies, and in these special energies, the transmission will be unity, and anything else, it will be below unity. Because you see that this condition is given by here. And what is this condition? This condition is given by, there are many such resonances. There's not one, there's not two. This is 2m E minus V, as the guy in the front row said. All this guy, what does it need to be that the sign will be 0? This is going to be n pi, and then n is equal 1 to etc. So there are many resonances. Think about this. A is fixed, although in some experiments you can change A. But let us think about it. A is fixed, M is fixed, H bar is fixed, V0 is fixed, and we change energy. So you can change energy, and then some energies will meet this condition. And in these energies, these are the energies of the incoming particle, then you are going to go, wow, everything goes back and nothing comes back to you. This guy, so let us write it as a function. What are these energies? So these energies, I can write E minus V. This is H bar n pi over A. Just moved it to the other side. And here I have 2. All this squared, 1 over 2m. Does this remind you of something? What does this remind you? I can't hear you.
Potential well.
What potential one? Infinite potential one. Yeah, that's what you meant. Good. 8a squared m. Especially this n squared should be familiar with you when you add a particle in a box with infinite potential. Here you have minus a. The energy levels were separated by an n square rule, and if you look at the units, h bar over a squared over m, these were the same prefactor that you had there, simply because you need a prefactor for energy which has the same units, and of course units of energy comes from h bar squared over a squared, that is momentum squared over m. This is the only way I can construct a scale of energy, so okay, this is not so surprising. So this is like a particle in a box. And then this means the following, that if you come with energies, this is E minus V, yeah? So I just subtract the energy. So it just means that in some sense that you have a resonance condition. You have here, I mean, you have some waves here which are commensurate with the size of this potential, because E minus V is like the kinetic energy. So what is happening here? You are coming, the wave function has changed. Now you still have a wave. That's why I draw something wiggly. This wave, it's not a square root of the K is not square root of E, but it's square root of E minus V, because part of it went into potential energy. And you are changing the wavelength, and the wavelength is exactly like a particle in a box. And you know what is happening for a particle in a box? It gets these zeros at its end. And when this wave, that means when you have this incoming energy exactly matching this size, you have a resonance phenomena and you can be transmitted. You should be, however, remember that I had in this expression, this was a sign. I can also look for the opposite case, where instead of saying the sign here is 0, I can say when is the sign equal 1. That will be the opposite effect in some sense. And this would also be a quantization rule. There will be some shifted thing. So it's not trivial, you know, that you get exactly the particle in the box. But just by shifting it a little bit, you get anti-resonances where you have a minimum, so to say. So sometimes this sign, we just choose to look at the Tmax. In a side remark, I don't know if you studied the scattering of classical waves from electrodynamics. You have similar things in electrodynamics when you have some medium here, and you have an electromagnetic wave, and then you have another medium in the middle, and then another medium, and then you have some wave. These are the waves that come in transmitted, and you have 3 different materials. So when the wavelength of the wave in not the quantum wave, the electromagnetic wave will have a resonance. Its wavelength will be such that we will fit the size of the scattering center in the middle. You'll have similar effects. So this happens also in an electromagnetic theory. It doesn't really help you because maybe you did not learn it, but maybe you heard about this, or maybe you will learn it soon. So you will see other effects in physics which are similar. What does this mean with respect to the transmission probability? So I can now summarize this. So how does the transmission probability? So again, this is the classical one, and this is as a function of E. This is T, and then I said I start here if this V0 is big. At the beginning, no way, I cannot tunnel, then it goes up. I get this point which we calculated, and then I get here these type of resonances. These are these points. I didn't draw it well, of course. What I was trying to do is these distances become bigger, right? Because of the n squared. The first guy is 1, and then this guy is 4, and then this guy is 9. I mean, this is the dependence on n squared. So this is the first resonance, the n equal 1, n equal 2, n equal 4. Remember, however, you see what happens also from here. Let's say this is a sine function. Let's take energy to infinity. What happens? You see this guy, just, he's dead. Here you have V0 is fixed, you have E minus V0, you have 1 over E squared. So at very high energies, you have resonances, but you can never see them, you cannot even detect them, right? Because the whole amplitude of the sine function is so close. So in practical terms, here you get what you expect, classical result. Because of this prefactor of the sine, which means, okay, t is equal 1 when energy is very, very big. It has these special resonances, but you see, if I have a resonance of my height and, you know, I do a fluctuation of sines epsilon, no one really cares compared to my size, which is roughly 185 centimeters, right? So it's a very small oscillation here. No one cares because no one can measure, because you always have some measurement problem. So these guys you can detect because it's reasonable. You can detect these resonances, but the further you go, it will be more and more difficult. And that is very natural, because what you are seeing here is that the quantum effects, the major quantum effects, happen in this region, in the middle region, where the energy is roughly the size of V0. Not too small, not too big. If they are too small or too big, you get here classical result and up here classical result. So this is also what you expect, and this is also what we find. Okay, so if you have no further questions, you have questions? If not, we'll continue, unless you want a break. You look a bit tired. You want a break?
I have a question.
Yeah, ask a question and then we'll have a break.
Okay. From the viewpoints of quantum mechanics, before measure the electron, it is just like a wave. And I mean, in quantum mechanics, I think maybe there is no such a conception as like direction. How can we imagine the electron goes from here to there like a classical wave?
Okay, so maybe I'll talk about it more next lesson, but first of all, you're right, because what do I have here? I have here a free wave. The incoming wave is EIKX.
Yeah.
And if I understand your question, the amplitude of EIKX is unity, if I take the square of this, and then the probability of finding the particle everywhere is a constant. So the particle, if you are in a free wave state, EIKX, what is your position? On average, well, you can be everywhere with equal probability. That's your question, right? So what we are doing now is we are solving these free waves. We are not solving a particle-like picture. So when you have a delocalized wave function, which is everywhere, the particle is more like a wave. That's why we call it a wave. But we can, in our imagination, and I will show you maybe next lesson more in detail, we have to start thinking about it also as a packet of waves, which is much more difficult. This I briefly explained at the beginning. But let me try to go into more detail. So you can say the following: I want to see the particle. Here I don't see any particle. That's a legitimate question. It's a good question. So in actual truth, the particle is always a wave. Yeah, I mean, you cannot avoid this waveness. But you can think about a wave packet. with, let's say, momentum h bar k0. Okay? I'm answering your question. This is what you ask, I think.
I mean, how to understand the probability direction.
Okay, so let me explain this in several ways. So in this wave packet, I have many waves, EIK0x times some amplitude. That's the main amplitude, and you have also other components. This is the G of k that we had. So this guy is now before feeling the thing is going like that, and the main center here is x p average. This is Ehrenfest times t over m. Now, in this packet, if you have a Gaussian packet, the main wave function is k0. So this guy is moving in the packet sense, on the average sense, with this k0, with this component in this direction. If you had a wave packet where this guy would be a minus and all the wave vectors, so you have a g of k, if you remember. The g of k in this example is centered around k0. And because all of them are positive, maybe you have a few negative ones, this packet is moving in this direction. Okay, so in that sense, you can see with your eye that the packet is moving in that direction, but there's not only one component of k0, there's also k0 plus delta k, minus k, etc. Okay, that's one answer to your question. The other answer is, I simply take the j, or I take the momentum operator and calculate, and then I get from EIKX, I get plus k times h bar. The problem with this explanation, maybe I'm going too far, is that what is the meaning when you have here some scattering? So this guy is slowly moving, and then it is spreading, and then it's reaching here. In this problem, you have, let's take three typical parts of the way. You have k0, then let's say you have k0 plus delta k, and you have k0 minus delta k. This is very rough. This is, let's say we take only this value and this value. Just to explain. I'm not doing the full math. Now, you say, okay, which part of the wave function will go through? Okay, first of all, what will happen? This will scatter here. It will be very complicated. It will look at when it reaches here, something horrible that you cannot calculate. You need a computer program even for this problem. But after some long time, you will see some packet going out here and some packet going in that direction. And this guy is reflected, this guy is transmitted, and this guy is reflected. So you have a Gaussian wave packet moving in that direction. It does something complicated, and then it's split into two. One going backwards, that's the reflected part, one going transmitted. Now you can define here the transmission probability, because now this is very natural, because all this guy is moving in that direction, all this guy is moving in that direction. The area underneath this guy is like a transmission coefficient, but this area is now composed of many k's. It's not one k like we had. But when is this area or this probability more or less the same as what we calculated? Can anyone say what is at all the relation between the two problems? What is the condition? So we calculated t of k, which is in our case tk0. But what will happen here? When will this t of k be the same as what we have calculated? The answer is simple. If t of k plus delta k is more or less the same as t of k minus delta k, and is more or less the same as k, that is, you work in some regime where this variation in k of the incoming waves that create the wave packet is not big, then it doesn't really matter. Then the transition which I calculated for 1k is good for this packet. You see this? But in actual reality, many things can happen because not always this condition holds. It depends. In other words, it depends how wide this delta k is. If you put in a very wide delta k, too wide in some sense, then you get all kinds of transmissions mixed inside your packet, and then you need to average. And then this problem of packets will be very different than free waves. What is that? So now you say, oh, I just made it more complicated. I did mathematically make it more complicated. This is much more complicated mathematically. But physically, the meaning of something moving, that was your question at the beginning, something moving and then moving back and then moving to the other way, where you can see, okay, you say, okay, the particle is more or less somewhere here. It can be also here, but you can see a particle in this picture. So physically, this picture of wave packets is, to some people, including myself, is more appealing. The problem is that mathematically I cannot construct easily this superposition of all the waves together. That's complicated. I cannot write it on the blackboard. What I can do, I can go for the break, I'll bring you a book and I can show you some pictures, how it looks, or you can go to the internet and you can see how you take a Gaussian wave packet and how it scatters on these potentials. And it's very rich. I mean, I just described some of the phenomena. You can have some potential like that. You can have a minimum of potential. You can start with wide wave packets, low wave packets. You can start far away or closer by. Very, very rich physics there is here, which we are not able to solve. And this is also true in electromagnetic waves, that you start with a superposition. On the other hand, the way you can see it in a real system is also, for this you need to know solid state physics in these systems, is that in solid state physics you have something to do with Pauli principle, that most of the electrons come with a Fermi energy level, specific energy they come close by to this, because they cannot occupy all energy levels. This is because of Pauli principle. And then they come with very specific energy, and then they are going into some sample. And if the energy fluctuation is small, which is the same as saying that delta k is small, then they have a typical energy, one energy, and they are free waves that are coming in, and then this is a good approximation. But to understand it deeply, you really need to go into the wave packet solution. Okay, so what we are going to do in the next lessons, we are going to solve, first of all, bound states of particle in a potential well. The problem is, the specific problem is, we'll have a potential like this, and we will look for the solutions of the time-independent Schrödinger equation. That is, we want to know how the energy levels of a particle in this type of small potential, how do they behave? What are the wave functions, etc. This is nothing to do with scattering, but it will have some connection to what we studied today, in that the classical motion, the particle can be only here, and what we will show that the particle can also tunnel into the region where it is forbidden to be classically, because classically it can be only in here, and you will have some amplitudes to be here, and this will call also tunneling. It's not a scattering, that you have something incoming and something outcoming, but it's just the fact that the particle can be in a region where it's not allowed classically. I mentioned this because I want you to read about this for the next lesson. We're not going to solve it Then after that, we're going to solve the time-independent Schrödinger equation for the harmonic potential. This is a particle in harmonic potential. Many textbooks deal with both these problems, so please read and then you'll be prepared for next lessons. What we're going to do now is something very general and which will help us in the future understand the solutions of the time-independent Schrödinger equation. And this is the following. So just a reminder. Up till now, we solved one problem, which was the particle in infinite potential well. So we had an infinite potential well, let's say from minus A to A. Here you had potential which was infinity. And let's call this point x equals 0. You can, of course, shift this box. It doesn't matter at all. But I want to now plot the x equals 0 as the point of symmetry of this potential. Now, we found the states inside here. So we had one state. This is the wave function of the ground state. It had little oscillations, none at all, one oscillation or half an oscillation. Because more oscillations means more kinetic energy. So this is the ground state solution. Then we had one solution for the first excited state, which looked like that. And if I go higher, I had more and more oscillations. We had the boundary conditions that determine this thing. Now, when you look at these functions, you see that this guy is an odd function. It's the wave function here is plus something, here it's minus something. It has a symmetry. Here it's a symmetric wave function. So this is something that we are claiming is general. Why do we find either even functions of x, that the value of the function here are the same, and here you find minus the function, etc. So this is an even function. This is the ground state. This is an odd function. And actually they come even, odd, etc., etc. Now, why did we find here such type of solutions of the wave functions? What is the reason? Well, what is this related to? It's related to the fact that the potential itself is symmetric. If I had a potential which was not symmetric, then this property naturally would not occur because there is no symmetry. So what you can already understand from this type of example is that if there is some symmetry in the potential, which means in this case v of x equals v of minus x, maybe we can show that this will be a general property that the solutions of the Schrödinger equation will either be even solutions or odd solutions. So when I say that v of x is equal to v to the minus x, it means that the potential itself, I call it an even potential. It's an even function of x. This means that, let's say this is my v of x, an harmonic potential. Or maybe this is another example. Let us say that the wave function in the ground state, the lowest energy value of the time-independent Schrödinger equation, is an even state. One can show this is correct. Then I already know, I know that this function is possible. This is a good candidate if I can prove that even solutions exist. Maybe this guy would be, this is a good function. But if someone guy comes and says, okay, the solution of the time-independent Schrödinger equation looks something like this. This is not even, this is not odd. You know that this is a wrong solution. This is impossible, provided that the potential itself is symmetric. And you see in all these examples, this is the potential. It's symmetric around this point, which I'll call always 0. So this is symmetric potential. This is a symmetric potential. And of course, there are many symmetric potentials in nature that I can build. So what I'm going to try and say is that the symmetry of the potential induces something on the wave functions, on the solution of the Schrödinger equation. And this is useful in many ways. Why is it useful? Because I can use the fact that, the wave function here is even, so it's also here even. So if I know it here, I know it there. Or if it's odd, then if I know it here, I also know it there. I can use it because I can disqualify certain solutions that I find by mistake. And more importantly, I can immediately draw in my mind, in the ground state, it's always an even function, more or less without doing any calculation, what is the wave function in the ground state. And this is our goal. Our goal is to be able to take some potential, and I tell you, how does the ground state more or less look like? You should be able not to know exactly the function, that can be very difficult, but you should know how, qualitatively speaking, these wave functions, let's say the ground state, the phase extent, look like in different potentials without doing any calculation. You have to build this intuition. This is important. It also says, for example, let us say that you have even odd or odd states. What does this say about the average position of the particle in these eigenstates? It's 0. So if the solution is either even or odd in the energy eigenstates, immediately you know something. On average, the particle in these states is smack in the middle where the symmetry of the problem is. This is why this is a useful thing. But it's more than that, because what I want to try to show you is how we deal with some symmetry in quantum mechanics and how we make this useful. And for that, we do some math. So I just want to first state the general statement, and that is for an even potential, which is binding, which means that at the infinity, I assume that they are bounded states, v of x equal v of minus x. Solutions of time-independent Schrödinger equation, H phi n. H is kinetic energy operator plus v of x. Let's say in one dimension you have one quantum number. Then you have either phi n of x equal phi n of minus x. These are even solutions. Or, for other n, and here you have the minus. So this is odd solutions. Only these type of solutions exist. So to prove this, we will define the parity operator. Parity operator is big P, not to be confused with momentum operator. This has nothing to do with momentum, big P. And the definition is that if you have P, it's an operator, and it acts on some function f of x, what does it do? It takes the x to the minus x. So this is an operator that acts on functions. It takes x to minus x. Just as a side remark, we have eigenvalues for this. Eigenvalues of this operator, this by the way, this is not something that you easily measure directly in physics, but this is important to take out of soon you'll see, using this operator to see what are the symmetries of the Hamiltonian, and this has the consequence on the wave functions. So the eigenvalues of this operator is some functions p plus, pi plus. So if psi plus is simply, this is an even function. So psi plus is some function. There are infinite amount of these functions. So there's one eigenvalue, but the degeneracy is huge in the sense that you can think of many, many functions like this. This is some function that just satisfies this. But all these functions, when you act on this like this, what will you get? You get the psi plus. So what is the eigenvalue? 1. So the eigenvalue is +1. This is the eigenvalue. The eigenvalues of this operator, when they are +1, and the eigenfunctions are all the functions which are even, but there is another eigenvalue. If I act on functions which are odd, then I get minus psi of x. So here the eigenvalue is -1. So in short, the eigenvalues of this operator capital P are either +1 or -1, and there's a huge degeneracy with respect to the all functions. It's not like we had here we had one energy, one eigenfunction. Here we have one eigenenergy and an infinite number of functions. So that means degeneracy. Many functions, these eigenfunctions correspond to one eigenvalue. Okay, this is just a side remark essentially. Now I want to work to prove this general thing. I want to define this thing. This thing is a projection operator. This is the name of this object. It's actually two operators, one with plus, one with minus. You see here plus and minus. What does this operator do? Let's say P plus acting on some function f of x. Now, every function f of x I can write as a combination of a even function plus an odd function. So when this is a statement, if you think about it a little bit, you will convince yourself that any function I can compose to a combination of the sum of two odd and even functions. Then I operate with P plus over 2. Then I have to operate first on the even part of this function. And then I have to operate on the odd part. What will happen when you take P plus operating on F plus? What do you get? You get +1. Because as I said before, when P acts on an even function, you get +1. What happens when you have P acting on F minus? I get -1. So what I get here is 1 + 1 over 2 F plus 1 minus 1 over 2 F minus. So this operator, this projection operator, takes you from a general function and it gives out the component of it, which is the even part of it. And similarly, if I act with P minus on f of x, which is a general function, I get out the odd part of the function f of x. So it's like so this is another operator. Now I want to show you that P plus and minus, either of them, H, is equal to 0. That is, the commutation relation between P plus and H is 0. We will my aim is to show that from this commutation relation, if you have some operator that is commuting with H, this means that you have some symmetry in the system. For example, you know this already with momentum operator with p squared over 2m. It would commute with one another. That would be like conservation of momentum in classical world. This would be commutation of momentum with an Hamiltonian without a potential. It will commute, and then momentum is a good thing that is conserved, etc. Now I want to show that these two guys commute, and from that we will show that if something commutes generally, but specifically this p plus and p minus, then I can reach some conclusion. That will be a theme that will be repeated many times. So let us do this for p plus, and I leave it to you to do it for p minus. So for what do I need to do? To show that this is true, I need to operate on some function phi. So p plus h phi. This guy is equal to p plus, let's write it like this, 1 plus p over 2. Let's write specifically the Hamiltonian, 2m dx squared plus v of x times some function phi. Now let us look. We have here 1/2. What does it mean that it commutes? That I can take this p plus and move it, that it will act first on phi. That is, switch the order of p plus and h. That's the meaning of something that is commute. Now let us look at this. This is divided in two parts. You have the 1/2. 1/2 is very easy to move out here. Why? Because this is just a constant. So I just multiply by a constant this half. It can be here or can be there. This is the usual multiplication that you know. What happens to p? So what does p do? Remind yourself, what does p do? It takes you x and makes it to minus x. Takes x to minus x. But what does this mean? If I have here x to minus x, I have here x squared. Nothing happens. If I have here vx, I take it to minus x, nothing happens if, and this is my condition, if v of x minus v of x, nothing happens. And p, of course, also operates on phi, but since it doesn't do anything, in other words, this guy is an even function, it doesn't do anything to this, it's even in x, then I can just simply take this inside and then write this as h p plus phi. And you see, if I add here a minus, it would be exactly the same, because I operated once with a half, one with a, this doesn't matter. So I can easily add also the pi minus, and then you see that we have shown that p plus h over some function is the same as hp plus. That means that they commute. This is a short way of writing this long thing. So what we see here, that the symmetry of Vx implies P plus minus H, because if this would not happen, and this will give you some conservation, some symmetry in the solutions. How does this happen? Let us show how. Again, I'll do it only for P plus, but it's the same with P minus. Why does this imply the general statement I gave at the beginning? So let us start with the Schrödinger equation in one dimension, one quantum number for symmetry, for simplicity. And now what I'm going to do, I'm going to act on this equation with P plus H phi n. Now, this is commuting. I can switch it because I just proved that I can switch this guy. No matter what was phi, I can switch it. So I can write it also like this. This is the commutation relation. Phi n. But this guy, if I look at this guy, what is this guy? This is also En P plus phi n. Now this En is the energy level. It's some number. This is equal En P plus phi n. So I just want to emphasize what is important here. I have H P plus phi n equal En P plus phi n. And that's it. Why? What does this equation tell you now? P plus is acting on some phi n. P plus is acting on some phi n. What is this function? This is by definition an even function. Even. So call this H phi even equal E and phi even. Why is this an even function? Because remember, what does P plus do? It takes a function, whatever it is, and it gets out of it the even component of it. Similarly, if I had a P minus, I'd have then an odd solution. So I have this, I prove to you this thing with this P plus. So there is some wave function, which is an even wave function that gives you this energy En. And similarly, you can show from P minus that phi odd is equal En phi odd. And this implies that either you have an odd solution or you add an even solution. That's all. So your solutions are either odd or even. I have to admit I didn't really prove this completely in a mathematical sense. I showed that there are solutions which are like this, even and odd, but I didn't show that they are a complete set. All this stuff I did not show, but we are physicists, so we will simply stop here and I tell you the no, this is an important question that is legitimate for mathematicians to ask. It's a fantastic question. Mathematical point of view, it's not something that we can put under the rug, but we don't prove this. This is proven by mathematicians that these are the complete set of all the eigensets. They are either even and they are either odd. You should understand this theorem. It's a small theorem, but as I said at the beginning, it will help you tremendously solve many problems in quantum mechanics, in even potentials. We always like to work with even potentials. Why? Because let's say you have a potential like this I can solve, like this I can solve. But do you think I can solve something like that? The answer is no, I can never solve it. So most of the potentials that we are able to solve have some symmetry in them. That's why they are easy, that's why we solve them in the classroom. So you better know this thing because these are the main examples in the next 3 lessons. These are the harmonic oscillator and the particle in the symmetric potential. This will solve, and this will be useful for us for the future. And please, I ask you again, please read more on the solutions of these 2 problems so you will be prepared for next lesson. Okay, so if there's no questions, I'll thank you and say goodbye for this week. Okay, thank you.